will discussing about radio broadcasting. Radio broadcasting is the transmission of audio signals to a large audience using electromagnetic radio waves. It is one of the oldest and most influential form of mass communication. Since the early 1900s, radio has played an important role in delivering news, entertainment, education, and emergency information to the public. Over time, radio technology has evolved significantly, starting for AM or amplitude modulation, then FM or frequency modulation, and now digital radio, which provides better sound quality and more efficient transmission. In this presentation, we will discuss the history, technologies, and current practices of radio broadcasting.
The heart of broadcasting is modulation. Audio wave from a microphone cannot travel far on their own, so we hit them onto a higher frequency carrier wave. In AM, the amplitude or height of the wave change to match the audio signal, while frequency stays constant. AM operates at lower frequency kilohertz, meaning it can travel huge distance, but it is highly susceptible to static and interference. In FM, the frequency changes while the amplitude stays constant. FM operates at higher frequency megahertz. It offers crystal clear, high fidelity sound but has a shorter range.
So, we have talked about how sound is created in the studio, but here's the million-dollar question. How does the sound actually travel from the microphone all the way to your radio speaker at home? It is not magic, it is physics, and it is happen by three ways. First step, it is transmission. Secondly, it is propagation, and lastly, it is reception. Let's break down each one. Firstly, transmission. Inside the studio, your voice hit the microphone and gets converted into the electrical signal. It is a weak low frequency audio wave. But here's the problem. The signal is too fragile to travel more than a few meters. So, the transmitter step in. Its job is twofold. First, it generates a carrier wave, a high frequency magnetic wave. Secondly, it modulates the carrier wave. Think of modulation like this. The audio signal is the passenger and the carrier wave is the vehicle. The transmitter makes them ride together. Once combined, it is sending powerful signal to the antenna, which radiates it outward as electromagnetic energy ready to begin its journey. Step 2. Propagation. This is where the wave actually travel, and it travel fast at speed of light, which is about 300,000 km per second. To put in that perspective, that signal can circle the earth over 7 times in just 1 second. Now here's something cool. Radio waves are electromagnetic, which means they don't need air to travel. They can move through the vacuum of space. They are just easily as they can move over our atmosphere. That's why we can communicate with the astronaut on the International Space Station ISS. The wave spread outward in all directions from the antenna like ripple in pond, and eventually a tiny fraction of the energy reach your location. Step 3. Reception. Your radio antenna intercept that incoming electromagnetic wave, but remember, it is still a modulated signal. The audio is still riding on the carrier wave, so the receiver perform the reverse process, demodulation. It strips away the carrier wave, isolate the original audio signal, and amplify it just enough to drive your speaker away. And finally, your speaker convert the electrical signal back into sound wave. Pressure variation in the air that your ear detect as music, news, or your favorite talk show.
Assalamualaikum. Now I'm gonna explain about the modern era digital radio and future. Radio technology has evolved from analog system to digital broadcasting. Digital radio such as DAB, digital audio broadcasting, and HD radio use digital signals instead of traditional analog signals. Before transmission, audio is converted into a binary code, which consists of 1S and 0S. This process allows digital radio to deliver clearer sound quality with much less interference and noise compared to AM and FM broadcasting. For advantage of digital radio, one of the major advantage of digital radio is its ability to reduce or even eliminate static noise. It also supports multiplexing, which means multiple radio stations can be transmitted on a single frequency, making spectrum usage more efficient. In addition, digital radio provides better overall audio quality than conventional radio system. Now, we move to additional features. Digital radio also offers extra features beyond the audio broadcasting. Listeners can view song titles, artist names, station information, weather updates, traffic reports, and news headlines directly on compatible receivers. Looking ahead, the future of radio is expected to be driven by the continued growth of DAB and HD radio technologies, along with the increasing popularity of internet radio and satellite radio. Radio services are also becoming more integrated with smartphones, smart speakers, and connected vehicles, ensuring that radio remains an important and accessible communication medium in the digital age.
In conclusion, radio broadcasting is a significant real-world application of electromagnetic wave. It involves key concepts such as AM and FM modulation, which show different ways of transmitting information using wave. In addition, wave propagation explains how radio signals are able to travel over long distance through the atmosphere. With the advancement of digital radio, sound quality and efficiency have improved significantly, although the same fundamental physics principles still apply. Overall, radio broadcasting clearly demonstrates how physics is used in our daily life, especially in communication and entertainment. That's all from us. Thank you.